Thank you very much. In this talk, we will take a closer look at Erlang OTP supervisors and how you can use them to make your application more well-behaved, not only in the face of error, but also under more normal circumstances that might, however, need some coordination. So I have been working as an Erlang OTP programmer for a very long time. And before I started to work for the OTP team, I worked as an Erlang consultant and trainer. And many times I found myself solving problems of process leaks, failing connections, and resource issues by creating Erlang OTP supervision trees or restructuring existing ones. But as in real life, you need good supervisors if they should help solve your problems instead of adding to them. So to be able to write good supervisors, we need to understand how they work. And to understand that, we also need to understand some basic concepts of Erlang OTP. So a basic Erlang process would look very much like this. That is, it would be executing code of executing the code of a recursive function. So let's call our recursive function loop, and we will give it a state as an input. And then our process will typically want to receive a message from another Erlang process. So we will wait for the message, and when we receive it, we will handle this request and generate a response, and maybe a new state. And then we will send an answer back to the process that called us. And we will call the recursive function loop. And then we go back doing it over and over again until maybe we receive a message that it's time to stop. And if it's time to stop, we won't call our recursive function. We will just not have any more code to execute, and the process will terminate in a normal way. Another property that we need to know about is that Erlang processes can be linked together. And this is a bidirectional link that can only exist in one instance. And if an Erlang process crashes, it will propagate an error signal to its linked processes that will then also terminate. Unless, of course, your process is trapping exit. Because if you are trapping exit and process crashes, the exit signal will be converted to a message. And now process 1 can decide, do I want to do some cleanup before I terminate? Or maybe I could survive that process 2 crashed. And also, how do we terminate processes in Erlang? Well, it's the most normal way that we have no more code to execute, and we terminate normally. And when we terminate normally, we will not crash our linked processes. And this is equivalent to calling exit with the reason normal. Okay? But you can also terminate another process in Erlang by calling the exit2 function. And then you need to know the process ID of the process that you want to terminate, and you can give it a reason why it should terminate. And there's also this special reason called kill that is not trappable. So if you kill an Erlang process, it will be unconditionally terminated, and there's nothing you can do about it. And if a process is killed that way and it's linked, it will have a special reason and its exit message called killed. So, as Erlang has lightweight processes as opposed to operating system processes, we can have many, many, many of them. But if we just spawn them, we have no control. So then we have our special processes, supervisor processes, that have the task of starting and stopping and restarting our processes, and they can supervise other supervisors or worker processes that do the actual work of our system. And most supervisors are going to be idle and hibernated most of the time, unless we need them to save the day. So I want to talk about links versus monitors. So as our supervision trees that build our OTP applications are built with links, we don't want to link to other processes on the Erlang node. Instead, we want to monitor them. So if you need to keep track of a process outside of your OTP application, you should use a monitor that is one-directional, and you can have many of them. And this could be another OTP application, or it could be a loose Erlang process. We have no control over that. And the real example of this comes from the OTP SSL application. So if we have a user process that wants to create an SSL connection to some web server, for instance, they will call our API function SSL connect. And when that happens, there will be 3 processes started under the SSL application supervision tree. 1 connection supervisor and 2 worker processes. 1 that handles the receiving end of the connection, and 1 that handles the sending end. And the receiving end also handles the underlying socket, and it wants to keep track of the user process. Because if the user process should terminate, we also want to terminate these TLS processes because they're no longer needed. So we don't want them to leak and be there in the SSL application. We want them to terminate. So how do we make a basic Erlang process become supervisable? Well, it needs to adhere to some basic concepts. So, for instance, you need to start your process by using the proc_lib library with the spawn link function there. And you also need to handle some system messages and system debug messages using the sys module. And preferably, you want your process to not do blocking things. And now they can be supervised. But of course, there is an easier way to make sure that your processes can be supervised, and it's to use one of our OTP behaviors to implement your process. So we have the gen server behavior to implement the simple request response handler. And if you have a more complicated process that needs to implement the state machine, we have the gen statem behavior. And we also have the gen event behavior that's targeted on dispatch processes. And I could tell you a little anecdote here that one of Erlang OTP's inventors, Joe Armstrong, he would say that we don't need all these behaviors and supervisors and stuff. This is so simple, we can just do it with Erlang. And even though he was a brilliant man, he wasn't always right. Everything is simple when you know how to, okay? So anyone here in this room, I think, could write the list reverse function. It's really simple. It's trivial. Yeah, there's an implementation here right on the slide. It works. I run it, so I know it works. But most of you are not going to implement list reverse by yourself, even if it's simple and you know how to, because you don't want to reinvent the wheel. You want to concentrate on solving your problem, right? And also there's other reasons to use our list reverse library, like you might gain optimizations that we have done, and you also get less code to maintain yourself. So, but let's get back to our supervisors. So supervisors also manages process dependencies. So a supervisor will start its children in a specified way. And when we started process number 2, it is a guarantee that process number 1 has run its init code. And if a supervisor stops its children, it will stop them in the reverse order. And the child to a supervisor is defined by what we call the child spec. So the minimal child spec has an ID, and the ID has to be unique for the supervisor, but it doesn't have to be unique for the supervision tree. And then we also need a way to start the child. Okay, so module function arguments. And then we have some additional things that we can say. We can make our process to be a permanent process. And this means that we want it to be restarted when it stops, independently of why. Or it could be transient. And then we only want to restart it if it stops in a non-normal way. Okay, so if it crashes. And we can also have temporary processes that shouldn't be restarted at all. And we can also give our child processes a timeout, so that when we say it's time for you to stop, they can have some time to stop gracefully before we brutally kill them. And there's also some supervisor flags that will define how your supervisor is going to work. And it has an intensity period. So like if you need to restart the child too many times under this period of time, probably restarting only this process is not going to help our problem. So then we need to escalate this higher up in the supervision tree. The auto shutdown, I will get back to that later, and now we're going to talk strategies in a moment. But first, so when you start an OTP application, like the public key application that doesn't define any processes, it's just a library application, the only thing that happens is that the modules of that application are loaded and they become available to other processes running in your Ally node. But if you start another application, such as SSL, that defines processes, when you start it, what happens is that you start the static part of that application's supervision tree. So, for strategies, so if we have the one-for-one strategy and process 2 crashes, only process 2 will be restarted. So an example of this is fairly high up in the SSL supervision tree. And we have a supervisor, and actually the TLS protocol comes in 2 flavors. So it's a stream-based flavor, which by default is run over TCP. And then we have another variant that is called DTLS, that is sort of a diff towards TLS, and it's datagram based, and it runs over UDP sockets by default. So these two type of connections has nothing to do with each other. So if we're having a DTLS supervision tree problem, we probably don't want to restart our TLS connections. And if we have the restart strategy one for all, and process 2 crashes, all the processes under that supervisor will be restarted. So a typical application of that could be an instance of a TLS server. So say we have a TLS server here that wants to support TLS 1.2 and 1.3 connections. And they need all these 4 supervision trees to function properly. And if one tree stops working, probably we need to restart the whole server instance to be able to get back to a stable state. And there's the rest for one strategy. So if process 2 crashes, process 3 that started after 2 and process 2 will be restarted. But anything started before will be left alone. So I don't have a good example for that one, but I think you understand how it works. And then we have a simple one-for-one strategy, which is actually an entirely different type of supervisor. And Elixir calls them dynamic supervisors, although it's not the supervisor actually that is dynamic, it's the children that are dynamic. And the children of such a supervisors, they are always started in runtime, and they are independent of each other, but they are running the same code, but with different initial arguments. And an example of this, simple one-for-one, also comes from the SSL application. So actually, it's a sub-supervision tree that is the same. So for each TLS connection, you will have this supervisor with the sender and receiver worker for each connection. And when you have such supervisors with independent children, you don't want this initial ACK thing that supervisors usually do to guarantee that the init function has been run. Because then you're sending a message back and forth, and you need to reschedule your processes. And this is becoming a bottleneck if you have tens of thousands of TLS connections. So you don't want that. So we can work around that by falling back on using the process proclib library to spawn our process instead of using the gen behavior function to start it. And then we have the gen enter loop, behavior enter loop, so gen statem enter loop or gen server enter loop to make our process enter our callback code. So supervisors, they will terminate their children by doing exit shutdown. And also in your behaviors, you can end your process by returning stop normal, yeah, or stop shutdown reason you can use. And that will also be viewed as a normal termination. So that you can have a graceful termination, but still have maybe a trace of why it was terminated, because there might be several ways that you gracefully want to terminate. Because if it crashes, of course, we can still be restarted and so, but then you will get an error report, and that you only want to have for unexpected things, not for graceful terminations. Sort of like I don't think that this certificate is okay, I will terminate the connection, but we don't want any error reports about that. So let's get back to the significant part. We've been talking about shutting down and restarting, but this all happens from the top of the supervision trees. You can only shut down your own process, but what if you want to shut down the sub-tree that you are part of from the worker? You can't actually do that in an easy way. There's a supervisor terminate child that you could call, but it's a call, so you will end up in a deadlock. You can't call this from inside your supervision tree. That needs to be done by some other process, if you might have some such need. But sometimes you want to initiate this shutdown from the children. So that's what a significant child is about, which is a pretty new thing. I think it's a 28 thing. Anyway, so if you have a supervisor with a significant any, and you have 2 significant children, and one of them terminates, then the whole subtree will terminate. And if you have significant all, one significant process can terminate, but you still have the other one as a backup, so you can survive it. An insignificant process can terminate, and it won't affect the subtree. But when all significant children, the subtree will be terminated. And this we use also in the SSL application. So the receiver process is a significant child. So if the other side shuts down the socket, yeah, we want the connection to go down. But if the sender goes down, we don't want the receiver to go down yet, because it might have buffer data that it still needs to deliver to the user. Oh, and this is a really new thing. Supervisor which child to, which is a very convenient thing. Because when starting up this supervision tree for the connection, I want my receiver process to know the PID of the sender process. And if I start it from the supervision tree, I really don't know that information. And I could register names for my processes, but that's not really an option for my tens of thousands of connections. So what I did before was that I started it manually. Okay, so because then I can get the PID of the first child and put it in the argument list of the start of the second child. The problem here is that now this code is not running in the SSL application. It's running in the user process. And the user process might crash in the middle of this. And now my supervision tree is not going to work as intended. And I might get a connection leak or a process leak. So my solution to that was to spawn a special process that would just set up this connection tree and then terminate. It works. It's not super nice, but it works. But with supervisor which child, I can now let the supervisor start my processes, and the supervisor can provide its own PID to the child that can ask, okay, the sender process, what PID does it have? So now I can start everything from my supervisor. I don't have to write any special code, spawning anything, or doing anything special, and I'm happy. So now that you know how supervisor works, let's summarize how they can help you save the day. So for the proper shutdown, here we have the significant child that can shut down the connection processes. And in the robustness case, we can also have a look at TLS 1 to 2 connections. And this is the typical receiver process, and it will perform a handshake, a full handshake, taking the blue path. But it could also do an abbreviated handshake once the client and the server has connected once, taking the red path. And this is done by saving some data on both the client and the server side so that we can do this optimization. Then we take, so we can't save any number of sessions because, well, we have limited space, but we will have a number of sessions saved. And we will take that session data and have a process handle that, and we will put it in a separate part of our supervision tree, not under the connection supervisor. And now let's say that we have a bug. So when we reach the maximum number of sessions that we save, the session handler crashes. And our supervisor will restart it with an empty session database. Okay? So, but this is pretty okay, because none of our connection processes went down, and none of our ongoing connections were really affected, because they can always fall back on making a full handshake. So the users will hardly notice. Maybe they are losing out on some performance, but the bug wasn't really hitting our system that hard. Of course, we want to fix the bug and have an even better performing system, but the supervisor saved our day. And the last example, this isn't a real application. I just wanted you to understand the concept. So we can imagine that we have some kind of HTTP server application. And of course, we can have many HTTP servers running on our Alag node, many instances. And let's say that a server needs the A, B, and C processes to work normally. So if we arrange them as on the left side, okay, you can see that if something happens in the server number 1 tree, this doesn't need to affect server number 2. But if we arrange it as on the right side, now things going bad in the supervision tree of A's might affect both servers, even if it was only one server that was failing, actually. So how you do it matters. So I'm not saying supervisors are magic, and I'm not saying it's going to be easy to do this for your application. I'm just saying that if you do it properly, it's going to be worth it.
Let's have some questions from the audience. And for the people online, please, again, use the Swapcard app to submit questions, and then we can read them here as well. 1 second.
Jeez. Thanks for the talk. I was wondering, the simple one-for-one, or Elixir Dynamic Supervisor, you said it's the same code, or the children are always the same code, but with different arguments?
Yes.
Do you know, is there a reason for that restriction to have, say it's always the same code for the children? Whereas normal supervisors, you can have any kind of child?
Yeah, well, it's because you can simplify the child spec, sort of. So they're always dynamically started, and the argument list is like hooked on later. And it's you also want to supervise those kind of processes. You want them to be part of your application supervision tree, but they don't have the dependencies that you want to handle when you use the other supervisors.
I have actually a question of my own, like using supervisors and the restart interval that you showed. Will we ever have like a debouncing interval, like something that gets longer when it retries? Or is there a reason we don't have that?
Well, we might have. I think even that Richard Carlson once tried to change how that worked, and I think there's reason to look into maybe doing that for real. And it wasn't that his proposal wasn't good; it was just that, like, supervision code is so old, and we have to be very careful with it to not break anything. And I think we need more priority from our product owner to work on it.
Thank you so much, Ingela. There's one more question. I'm coming to you.
Just really quick, because I got confused about this, and maybe others too. You quickly mentioned there's a, in the init phase of the process, there is a ping pong between the supervisor and the child process to make sure that it actually boots up properly. But as I understand it, it's optional. So if I'm right, how does the supervisor know if the child is actually talking this protocol with it? Thank you.
So you mean that if I'm a child process and I want to shut down my supervision tree?
No, startup.
Oh, at the startup. Yeah. Well, we you know, you have the application behavior. So if you do an OTP application, you have to have a callback for the application start. And there you will start your top supervisor. So the application start, you know, what is the top supervisor of the application, and the OTP will, or Erlang OTP will start that, and then the supervisor will start the rest of the tree. I hope that answered your question.
If not, you can find Ingela also afterwards. Yeah. Maybe one more pitch, just like if I prototype my small app, why should I start with supervisors?
Well, it's like you are going to need them, but you are not going to realize that at the start. But it's like security. It's much harder if you try to put it in afterwards.
Thank you so much, Ingela. Please give her warm hands.